What is KEMi? We are the Kren Engineer-Based Medicine Initiative. We're catalyzed by a very major gift from Mr. and Mrs. George and Martina Kren. And we have the big vision of transforming health and healthcare of the future using engineering and innovation. And we're brand new. We're only a few months old, and yet we're already funding faculty and students at University of Washington. So good afternoon, distinguished guests, colleagues from University of Washington and University of Nottingham, and our audience around the country online, as well as from the United Kingdom. Welcome to the inaugural KEMi special seminar coming to you at Seattle at University of Washington. My name is Tong Shen. I'm the Associate Dean of Medical Technology Innovation between UW Medicine and UW College Engineering. So on behalf of KEMi, now you know what it stands for, I really thank you for all of you to take the time out of your busy schedule to join us for this very special occasion. And I would like to first thank George and Martina Kren, who's joining us online from Monterey, California. And I also, of course, love to thank especially the force behind a lot of the activities, long-term UW donor, Graham and Brenda Siddall, who is sitting with us in person in this auditorium. And I also like to extend the warmest welcome to President and Vice Chancellor from University of Nottingham and your delegation to visit University of Washington. And there are many of you and a lot of our friends and donors who come today, and I really appreciate your support before we start. Because this is the very first inaugural KEMi special seminar, I feel it's very important that I share a little bit of background about the initiative before I introduce the speaker. And like many of us coming to the United States to seek American dream, George came to the US in 1974 from Prague, and he soon, as a brilliant engineer, started a company with his high school friend called Tanker Instruments. As a pioneer and key innovative mind for the company, George made a successful career. And these innovations actually made critical impact for the later information technology. And George's connection to UW actually is through his longtime friend, as I mentioned, Graham Siddall, Dr. Siddall. And I like to share with you this history book of Tanker Instruments. And the first chapter's title, Immigrants and Friends, really had deep resonance with me as an immigrant myself. And George and Graham had known each other for almost 40 years. George founded the company, and Graham later was recruited to lead the company. Both of them, you will find lots of stories to share from Graham, how they made a successful business. And this accelerated to today. 40 years later, they are still good friends and start chatting about new things to do. And I think that you can imagine that how privileged I am and have a close relationship and interactions with both Graham and George, not just as a physician and as a fellow engineer, but also as their good friend. Especially recently that we spent many long hours, Graham would say hundreds of hours of talking together to map out the future of KEMi. And I think these relationships that inspire us all to think big and think for the future. And I think that the commitment of George and Martina Kren and also the energy from Graham really galvanized a huge momentum at UW for KEMi. So we see commitments from administrations, from our faculty. We see deans, for instance here, Tim Dellett and Nancy Alberton working together during the day. And then you see the vice deans, Jiwei and Shelley working on weekends, ironing out what's needs to be done for KEMi. And more importantly here, just to put this seminar together, we had a very short, running time. So Amy and Sheree, one from school of medicine, the other from college engineering, working together and with our photographers, with our AV. You can see that on the picture. Amy and Sheree were wearing two different sets of clothes because they have come more than once just to make sure that the online streaming is working and everything else is working. And the backdrop that you will see on the reception came just in time for us to take photos with our KEMi investigators later. I think this spirit really is infectious, and it allows us to really ramp up KEMi very quickly. So when Graham came up the name KEMi in May, we actually sent out the call for proposal just about a week later. We gave our investigators 2 weeks to respond to this call for proposal. Requirement is one clinician, one engineer. And we thought 2 weeks, what can we get? We got 83 proposals. So I think Shelley and Jihui had the difficult task of picking all these excellent proposals within a very short period of time. And by July 1st, we have 10 programs up and running. And these programs ranging from robotics, ranging from emergency medicine, ranging from ophthalmology, and it could be biosensing. So you can go online to our website to learn more about these projects. But what a quick 2 months that we're able to do. So I wanted to extend our congratulations to the first KEMi investigators. I have some labels of KEMi investigators. If you're in the audience, please stand up, receive our congratulations. Congratulations for your accomplishments. Thank you. And I hope that we can really use this momentum to really take the inspiration for this remarkable friendship and generosity, allow us to rethink what academic medicine might be. And I think our journey has just begun. Thinking about the combining the talents of our faculty and students and the resources from our community, I think our future is boundless. So with that said, now I'm going to switch gears a little bit about today's seminar, because this is a first special KEMi lecture, and it just happens that we are, based on the connection of Graham again, coincide with the visit with University of Nottingham. So we appreciate President Jane Norman here with your delegation. And today is the second day of this program. Yesterday, in partnership with iLabs, with Pat Cole, we had a lot of really interesting, engaging, stimulated discussions about brain imaging and MAG. And today, we're going to switch gears a little bit. Again, still using the expertise from our Nottingham colleagues. At the risk of disclosing how old I am, I still wanted to use this, this little story I used for my MIT PhD thesis on MRI imaging and contrast agents to tell you about the topic of today. So this is a legendary healer in the ancient fairy tale. And the healer was known to be extremely versatile in terms of diagnosing diseases and treat problems. And one of the secret is that he had a pet lion. And this lion supposed to be completely transparent. So the healer could look at the lion through the body to see where the problem might be, or testing for treatments for herbs. And in that sense, he actually helped a lot of people. But one day, this lion disappeared. So a lot of the statues of the lion are all over in the pharmacies and clinics because they wish it will come back. So I think the modern technology has brought it back. So if you think about MR imaging, so MRI, this word, when I was doing the research in 1980s, late 80s, it was not in the vocabulary of clinical medicine. But today, it's used every single day that transform how we take care of patients and how we manage disease and doing diagnosis. So I couldn't find a better person who's going to tell you the story about how this magical lion's been brought back using innovation in engineering and technology. So today, it's fitting for the goal for the special KEMi seminar. We really wanted to look for transformative technologies to improve medicine. And I would like to ask you to join me to welcome the Professor of Physics and Director of the Sir Peter Mansfield Imaging Center. He will tell you a lot of the stories about how this is coming about from the United Kingdom. Professor Richard Bowtell.
So I'm going to tell you something about magnetic resonance imaging. Obviously, a good starting point. I understand there may be some people in the audience who aren't so familiar with magnetic resonance imaging. So a basic introduction to the technique is that it's a technique that uses strong magnetic fields and radio waves, and that gives us signals which come from atomic nuclei, mainly the nuclei of hydrogen, and it's globally used today in about more than 60 million medical examinations every year. And I suppose the reason that I'm here is that it was co-invented in Nottingham University. And I guess I'll tell you a bit about some of the past development of MRI, which happened in the Department of Physics in Nottingham. I'll talk a bit about some of the current work going on in MRI, which I'll frame around the work in Nottingham, but hopefully go a bit broader than just that. And then talk a bit about the future of MRI, again, maybe focusing mainly on the areas that we hope to be taking forward in Nottingham. So just a brief introduction to what the origin of magnetic resonance is, to give you some understanding, the people who haven't worked with this technique. So it's based on a phenomenon of nuclear magnetism. And that arises because the hydrogen nucleus has a positive charge, and it also has intrinsic spin. So we can view it as being like a spinning ball of positive charge. And moving electric charge, I'm sure many people know, is an electric current. And a circulating charge is like a current loop. And you probably know that a current loop will generate a magnetic field, has a particular form. It's called a magnetic dipole field. And it's actually very similar to the magnetic field produced by a bar magnet. In fact, it's identical if you shrink the magnet down in size. So we can make some progress in understanding magnetic resonance by using this analogy. The thing is, of course, that magnetism coming from a hydrogen nucleus is very, very tiny compared with the magnetism of a bar magnet that we might be able to hold in our hand. But we have the advantage that when we're trying to measure signals from hydrogen magnets, that there are a lot of them. So in a typical 70-kilogram person, there might be 10 to the 27 hydrogen atoms with nuclei that we can potentially measure a signal from. If we could take someone and shield them completely from a magnetic field, then the hydrogen nuclear magnets would just be randomly aligned. But if we place someone in a magnetic field, then like a compass needle, the hydrogen magnets line up with the magnetic field. And then collectively, their net magnetization acts together to produce something that can make a measurable field. Sadly, it isn't quite as good as it looks in this picture, in that we have to call on quantum mechanics and statistical mechanics to really understand what's going on. And it turns out that we actually end up with, in general, equal numbers of the hydrogen nuclear magnets pointing along the field and against the field. But there is a small excess. If we take a typical magnetic field used in MRI, about 1 in 100,000 more pointing along the field than against the field. And because we have 10 to the 27, of these hydrogen nuclear magnets, then we still are in a good place to get a measurable magnetization that can give us a signal. To understand the signal, the generation of the signal, you have to know that as well as the spin, you have the magnetic moment. And so you have a system like a gyroscope, which has intrinsic angular momentum, and you have a couple on it in the case of the gyroscope produced by gravity. It can't fall over because it has to conserve angular momentum, so it goes into a precession. And the nuclear magnets behave in the same way. They will experience a torque, right, which will try to realign them with the magnetic field. They can't just realign because they have to preserve angular momentum, and hence they precess around the field. And in the case of the hydrogen nuclear magnets, case of nuclear magnets, the frequency of precession is proportional to the field strength. So the stronger the field, the faster the nuclei will precess. So as we're sitting here in the Earth's magnetic field, 50 microtesla, the nuclear magnets are precessing around in us at about 2 kilohertz. So it's a nice, steady, smooth frequency. So to interact with the nuclear magnets, we need to have some way of disturbing them from being lined up with the field and making them then go into this precession so we can measure a field. And the way that we can do that is by applying electromagnetic radiation, which is essentially tuned to the frequency of precession. So if we do that, we disturb the nuclear magnets and they start to precess, and we can measure a signal. So we get a coherent signal by essentially surrounding our sample, the human body usually, with a coil of wire. And of course, if you have a changing magnetic field inside a coil, you will then get induced voltages through electromagnetic induction. So we see a weak voltage across the coil, which tells us about the precessing nuclear magnets. And the frequency of precession increases if we increase the magnetic field. So we can measure the field actually very accurately by measuring the frequency of precession. And our signal actually goes up twice as fast as we might expect as the square of the magnetic field, because the magnetization scales with the field and the frequency of precession also scales with the field. So as a sort of simple introduction to where the signal that we use for MRI comes from, we have to, for those who are expert, when we look at the real evolution of the magnetization, which is what will decide the way our images look, it's more complicated, and it's described by this Bloch-Torrey equation. But I just wanted to show that to indicate that there are lots of things that can affect our signal in MRI. If we look at this equation, we have here a magnetic field, a local magnetic field, and that can be sensitive to the presence of magnetic inclusions in the object. It can be sensitive to hemoglobin, which is magnetic when exposed to a magnetic field. So that gives us a way of looking at sort of the chemical environment and maybe also at microstructure. We also have sensitivity to what are called the NMR relaxation times that dictate the recovery of the magnetization to equilibrium. And these are really sensitive to molecular motion, and they're sensitive to the presence of paramagnetic compounds like are used in contrast agents, and they're sensitive to binding and exchange. So it's really a rich source of contrast. And then we also have sensitivity to motion of the molecules carrying the nuclei that we're getting signals from. So we can measure diffusion, that tells us about motion of molecules, tells us about microstructure that blocks the motion of the molecules. And also, we're sensitive to coherent movement in flow, which gives us a sensitivity to blood flow, for example, or the sensitivity to the CSF flow. That is a very exciting way of looking at the glymphatic system, as is pioneered here at University of Washington. So that was what underlies our beautiful contrast in a magnetic resonance image like this one. So we see in this particular one, we're very sensitive to the local magnetic fields, which come, in this case, from the deoxygenated blood in these primary intercortical veins in the cortex, in the gray matter at the surface of the brain, and that reduces our signal. Okay, so finally, in this sort of introduction, so I've told you how we get a signal. I've said it's a very rich signal, but how do we make an image using that signal? Well, so the intrinsic problem is if we have a very simple object like this, and we just measure the signal from these two regions of the object in a magnetic field, the signal will look the same from those two regions because the field in those two regions is the same, and therefore the frequency is the same. So that's no good for spatially resolving the signals from the two eyes in this case. But if we apply a magnetic field, an additional magnetic field which varies with spatial position, then we can make the frequency of the two signals different because the magnetic field experience at the two locations is different. And now if we can frequency analyze the signal, which is very easy to do with a Fourier transform, then we can work out how much signal is coming from each location. So that is the key to magnetic resonance imaging. Use spatially varying fields to encode spatial information in the signal. And that is the idea that Peter Mansfield came up with in 1973. So he was actually a physicist working in solid state NMR to understand the atomic structure of solids. But he was, to demonstrate his idea, he did a very simple experiment with a set of 3 layers of camphor. It's a kind of waxy solids in Vicks rub, if anyone knows that. And when he saw that when he applied a gradient, he could produce 3 peaks in the signal that correspond to the 3 layers of camphor. And when he had 5 layers, he got 5 peaks in the image. So, spatial information encoded. At the same time, Paul Lauterbur in Stony Brook in the US probably took things further and made an image of this very simple phantom containing 2 tubes with water in, and that was published in Nature in 1973. So that really stimulated a lot of interest, but in the early days, there wasn't a huge community of people working in magnetic resonance imaging. This is the first international conference on MRI in Nottingham in 1976. So for the Nottingham people, it's outside the Hemsley. So it's an interesting picture because in the middle of the picture, there are together 3 Nobel Prize winners. So happen to congregate at that place. So that's Paul Lauterbur and, sorry, just going back. So that is Paul Lauterbur here, Peter Mansfield, and Richard Ernst, who actually won the Nobel Prize for chemistry in the 1990s, but did early work on MRI. So that's Peter Mansfield and Paul Lauterbur getting the Nobel Prize in 2003. So another interesting point is that it's a small group of people working on MRI in 1976, and actually there were 3 independent groups in the Department of Physics in Nottingham who were working on MRI and not always working together, so in competition with one another. So actually about half of the people in this picture are from Nottingham. So that was a nucleus of the work. Raymond Andrew went to the University of Florida in the early 1980s. Bill Moore went to Harvard and sort of seeded activity in other locations. A little bit about Peter Mansfield. He was born in 1933. He had a very non-standard, I guess, trajectory into academia. He left school at 15. He worked in a print shop until he was 18. And the legacy of that was when we had papers corrected, they were always very well set with proper sort of markings on them that we all benefited from. He worked on a rocket program. He got onto a rocket program. He did national service. He took A-levels at night school. He then did a degree in physics. He worked with one of the early pioneers of NMR in the UK, and he discovered new phenomena in solid state NMR, and that led him to become a faculty member at the University of Nottingham and to then invent MRI, become knighted and win the Nobel Prize. So just to say, this still image is actually from Tomorrow's World. Some people may remember that in the UK, sorry. It's a famous science program. And I have a video, which I won't show now, which is of from 1976, which is a really amazing sort of historical document of how Nottingham University was at that time and the work of Peter Mansfield. So just to say that I think it's clear that Paul Lauterbur had the first real image, but Peter Mansfield justifiably shared the Nobel Prize because he made many contributions which actually meant MRI became possible. So from physics and engineering ideas, he introduced the concepts which really made MRI take off. And that was recognized in the Nobel citation. For those who know, just to say the great use of gradients, he came up with slice selection, he came up with echoplanar imaging, which is used in all fMRI experiments. And he came up with active magnetic shielding, which is used in all scanners pretty much. So just to say, I joined Nottingham in 1984, and this is where I had some involvement in work in active shielding. So those techniques have brought us to the point where images, in 1977, difficult to see the anatomy. Nowadays, obviously very clear in the body, the anatomy. Just to say also that in those early days, you couldn't buy a scanner. So he built the first whole body MRI scanner in the physics department in Nottingham. Later on, built the 0.5 Tesla scanner using a first superconducting magnet, built an NMR microscope working at 11.7 Tesla. Later, we built the first 3T scanner. So there's a long history of building systems with engineering and physics expertise in Nottingham, which has carried on with our work at 7T more recently, and the development of the wearable MEG scanner that you heard about, some people heard about yesterday. And as I'll talk about a bit later, also the plans to install and develop an 11.7 Tesla scanner in Nottingham coming on. So a bit now into the present day, what is our centre? So, well, we began moving out of the physics department in 1991 to build that 3 Tesla system based on largely funding from the Department of Health in the UK and the body who administered the patents that Peter Mansfield had taken out on his early developments. And then after the Nobel Prize was awarded, the centre was renamed to Peter Mansfield Magnetic Resonance Centre. And then a bit later, we combined together the activity in physics with the leading activity in medicine, where there are also some scanners for research in the hospital, to form the Sir Peter Mansfield Imaging Centre as an interdisciplinary cross-faculty centre. So today we have 26 academic staff across a variety of schools, as you'll see, and we are very much cross-faculty as an entity. There are a lot of students across the various departments who use imaging as their main focus, and we're part of a number of centres that are national and international. And we operate a range of imaging systems as a facility for the University of Nottingham, as I've seen sort of similarly very important facilities here at University of Washington. So on the University Park side, we have a couple of human imaging systems for MRI, and we also have the OPM MEG facility, which we'll talk about later. And in the Queen's Medical Centre, we have a 3 Tesla system and also a slightly non-standard system, which is a vertical MR, which I'll tell you a bit about shortly. So we have a lot of faculty, and I wanted to sort of use their research as a way into describing the current state of research in MRI, but they cover a very large range of different areas of interest. A lot of physics and engineering, but driven by application in a wide range of areas in the human body. So I just picked a few different themes, which hopefully will illustrate some of the work in Nottingham, but also some of the themes in MRI, which obviously chime with what we're doing. So I've picked out first sort of quantitative MRI, the measuring not just signals, but trying to convert those signals into numbers that can be consistent, more consistent, hopefully across different scanners. So this is the work of, what I did there. Oh, that's fine. Thank you. So this is the work of Sue Francis in Nottingham. If I click there, will that? Yeah. So who is an expert in renal MRI? So measuring signals from the kidneys and images of the kidneys is very good with MRI, and I guess it complements other measurements with ultrasound or with biopsy. But the nice thing about MRI is that you can use that rich capability to measure lots of different quantities that tell you about the environment of the hydrogen atoms in water or in fat. So an example is a 1 hour non-contrast scan for making quantitative measurements on the kidneys, which Stu has developed with colleagues. So initially for measuring morphology with weighted scans, and which can measure fat signals separately from water signals, and then scans which are particularly focused on measuring microstructure, so with diffusion imaging, with magnetic resonance elastography, and mapping those relaxation times, and then looking at hemodynamics by measuring effects of flow, and then measuring oxygenation by looking at the effects on the relaxation times. So it's a powerful approach, which with colleagues she's applied in looking at disease. So the example here is measuring one of those relaxation times, the T2 relaxation time, to quantify tissue composition, to then look at changes when there are inflammation and edema. So one thing with MRI is that there are many different ways of measuring these quantities. There's a whole range often of different sequences with different acronyms for sometimes different vendors who sell MRI systems. So an importance now is, of course, to try and harmonize across different systems so we can relate quantities, and measuring quantification obviously helps with that sort of comparison. So in this work, there was a process of optimizing the measurement sequence to find these changes in T2, to harmonize the sequence across different scanning platforms, and then to accelerate the imaging so that measurements could be made in a breath hold, and then application, in this case, in looking at different types of renal carcinoma in this paper. So hopefully an example of where quantitative MRI can, with involvement of, I guess, physicists and medics in optimization of sequences, can then be rolled out in application. And then say a little bit about some somewhat related work in imaging of placental function carried out by my colleague Penny Gowland. So MRI, I guess, isn't commonly used in obstetrics, but it does give very nice images. This one at 3T showing the fetus and the placenta here. So Penny has also used quantitative measurements to try and understand the blood flow within the placenta, particularly looking at the maternal blood into the placenta. So here in the placenta, these maps are telling us about the oxygenation, which is coming from measurements of the effect of local magnetic fields and T2 star, and then measurements of flow, which gives some insight into the form of the pattern of flow within the placenta. And she's used that approach to start to try to understand a different kind of contraction in utero, which occurs in sort of more locally than the more standard Braxton-Hicks contractions. So a local contraction of the placenta linked to the placenta and the wall of the uterus just locally rather than more collectively. And that's now being looked at in terms of differences in the frequency of those contractions in compromised pregnancies. Moving on to exploitation of quantitative MRI measurements. This is work of a colleague, Stan Soteropoulos, who already has collaborations here at the University of Washington with Ariel Rokem and others. So his work is really in analyzing diffusion MRI data, particularly to understand the connections in the brain. So here, looking at the connections between different areas of the brain in the fiber tracts of white matter. And these are some of the measurements that he makes in order to produce these beautiful maps. So just to flag up, one recent piece of work that he's done, I believe is sort of similar emphasis on the effects of COVID in the work of Pat Cool's group and others. So this is using data from the Biobank in the UK, where you probably know a large cohort of people have been scanned over time. And as part of this, a smaller number of people have been scanned twice. So with a separation of about 2 years in the scanning. And so from this data, people have found features which correlate with age in the brain. And what they were able to do was, because this study was progressing during the pandemic, they were able to compare people who were scanned approximately 2 years apart before the pandemic and then across the pandemic. And then using the analysis in this case, 500 in each group, they were able to identify factors which actually cause an acceleration of brain aging in the group which was affected by the pandemic. So these looking at the effects of demographics on the rate of acceleration of the brain aging. So I guess an example of where these quantitative MR techniques are being used at scale and can give really important information. An example of some new technology is this upright system that we have, a slightly unusual magnet. Normally magnets are superconducting and have a cylindrical bore. You go inside, as you probably know, lie on the bed. This one is a different kind of magnet, has no helium inside it, which is quite useful in these days, and it uses a novel superconducting technology, magnesium diboride. And the interesting thing about this system is it's relatively low field, and it allows you to make measurements with people in different postures, so lying, sitting, standing, etc. In this example, they were looking at the effects of posture on, I guess, the motion of the lung and also the ventilation of the lung, seeing small differences for effects of posture. It can also enable studies like, I guess, proctography, which is sometimes done in MRI with people lying down, but obviously a more natural posture to do that is sitting down. And so that is important for understanding defects in the pelvic floor. So just to say another interesting point linked to novel technology is, if we look at the lungs in these images, you can see there's not very much signal coming from the lungs because they're mainly air. The amount of water is relatively limited. There is some signal that we can obviously exploit. But if we could measure a signal from the air in the lungs or the gas in the lungs, that would obviously be give us maybe more of an indication of lung structure. So there's no accessible signal easily from air, but noble gas isotopes, helium-3 and xenon-129, do give us an NMR signal, and potentially we could make a measurement with them. But the problem is that if we look at our simple picture of what's going on in a liquid, we have a high density of atoms and therefore of the nuclei. But in a gas, the density is obviously much, much lower. So our signals are going to be much lower unless we do something about it. And one idea is to use laser polarization. So actually a technique very similar to what controls the operation of the optically pumped magnetometers that are used to measure brain activity. And by essentially exciting electron transitions, you can get almost a full polarization in these gases. And you do that in an external system, and then someone will breathe in that gas in a bag, and then you can make images, in this case, where you see signals that coming directly from the gas. So that's interesting work being done by Thomas Mearsman and Galina Pawlowskaya in Nottingham. And they've also been applying that and looking at the effects of lung damage from the pandemic, from the effects of COVID, because one can actually look at xenon signals coming from different environments that tell you about the amount of thickening of the walls of the alveoli. So just to look at another example where this is obviously an example where we're measuring a signal that's coming from something that isn't hydrogen, in this case, xenon gas, but there are actually quite a few other nuclei, isotopes effectively, which give us a signal that we can make an image from. So an example here would be from a signal coming from phosphorus in the liver and being used to look at a response to a sugar challenge and correlating that with the effect of body mass index. Or another example would be to measure a signal from sodium, which is accumulated in the skin and can tell us something interesting in effects of dialysis. So the example I was actually going to take one more of a minute to look at is looking at deuterium. So that's an isotope of hydrogen. It's very uncommon in natural circumstances, so 15, 16 parts per million in natural circumstances, but that means it gives a very low signal. Typically, it has a weaker magnetic moment. So the signal we might measure, just if we put someone in the scanner straight away, would be quite small compared with that from water, from hydrogen, normal hydrogen in water. But if we give someone a labeled compound, then we know that the signal we see must come mainly from that labeled compound. So there's some interesting and exciting work going on in using deuterium labeled glucose to try and look at metabolism, glucose metabolism in the brain. This paper from the Yale group was very exciting in identifying effectively the production of lactate in tumors, stimulated a lot of interest, which is being followed up by groups around the world. So they were able to, I've done the same thing again. They're able to identify the tumor in terms of the lactate concentration. So I just mentioned that, if I go there. Yeah, we have done some work in looking at heavy water loading. So people for, metabolic studies involving biopsy, people often load with heavy water. So they drink heavy water to produce maybe 1% concentration of heavy water in their body. And that's enough to actually produce quite a strong deuterium signal for us to measure. So we have measured the effects and the time course of someone drinking deuterium labeled water in the magnet, where you see the increase in signal as the labeled water is transported to the brain. The time course seems to mainly be dominated by absorption in the stomach, but there could be interesting ways to take that forward with the injection of the labeled compound. The time constants are sort of 6 minutes or so for absorption in this case. So finally, in the present, just to talk about some work at 7 Tesla. So probably know that most scanners in hospitals nowadays operate at 3 Tesla as a magnetic field. We have a 7 Tesla system in Nottingham, which we've had for some time. And the reason we have that is that the signal that we get goes up very quickly with the magnetic field because of that increase in the magnetization and the rate of precession. And so that gives us the strong signal that we can then use to improve the spatial resolution of our images. We have more signal, we can look at smaller volumes to make the images make each point in an image. So an example of the exploitation of that was work by colleague Nikos Evangelou, who looked at measuring signals from lesions from multiple sclerosis at 7 Tesla. And he identified that for lesions, in the case of multiple sclerosis compared with other lesions, there was a signature generally of there being a vein within the lesion. So it became known as the central vein sign and is now being considered as a biomarker for multiple sclerosis. So in the last 5 minutes to move to looking to the future. So there are obviously a lot of exciting things still going on in development in MRI. So even more than 50 years on from its initial invention, there are still new ideas coming through. It's partly because of the very rich nature of the signals we measure, and because of the engineering expertise of groups around the world. So some of the areas I highlighted, I picked out are, I guess, high field, low field, midfield, still interest in these different fields, strong gradients, sustainability of scanners, being able to scan in a way that doesn't depend on whether you're using a Philips or a Siemens system, so vendor neutral scanning, reproducibility of always important, and some of the things that we've looked at. And of course, AI is having a huge impact in the image arena. But I'm going to focus on high field MRI and on multimodal imaging. So I wanted to just bring in the OPM MEG developments, just to tell you a little bit about that. And then I'll tell you mainly about the plans for this 11.7 Tesla scanner. So what is this? It's a plan to develop a national facility for ultra high field scanning in the UK. And it's going to be an open access centre. It will be in Nottingham at the Sir Peter Mansfield Imaging Centre. And it's a bid that was developed by across the UK MRI community, but the decision was to house it in Nottingham. So what our aim is to make a scanner which will allow us to assess brain function at a mesoscopic level, to make anatomical images with histological detail, to provide unique measures of organ metabolism, and to form a platform for developing new technology and methodology for MRI, which will hopefully be applied at not just at very high field, at lower field. So we're sort of following in the footsteps of the development of measurements using magnetic resonance. So in the case of analytical systems and preclinical systems, there has been over time a move to higher magnetic field, which is echoed in the human domain, with people, as magnet technology improves, moving to higher magnetic field. And the reason is, of course, that gain in signal to noise ratio keeps going as you go to higher field. So we would hope to get a 9-fold gain in signal to noise ratio as we go from 3 Tesla to 11.7 Tesla. And there is a system in operation working at this field, which is in Paris at a CA site, the Neurospin, and they have produced their first images at 11.7 Tesla, which provide a lot of confidence that it's possible to get really beautiful contrast at this very high magnetic field in the brain. So an area which will be very important for application of the system is in measuring brain function, because over and above the gain in intrinsic signal that we get by going to higher field, we also get a gain in sensitivity to blood flow changes in brain function, which further enhance the signal we measure. And that's allowed at 70 measurements of activity in the brain with very fine detail. So resolving not just the representation of the hand, but the representation of the different parts of the hand along, say, just one finger in this sort of study. And it's already been shown by the Minnesota group working at 10.5 Tesla that there are significant gains compared with 7 Tesla. So comparing, say, these data, you can see that the activity in orange and blue is more clearly revealed at the higher magnetic field. So we're very excited about that development, but also, of course, excited about the OPM MEG development. So that's measuring the magnetic fields outside the head produced by current flow in neurons in the brain. Conventionally, that's done using a squid-based measurement system, which requires liquid helium, is very heavy, not movable. This uses an optical sensor, which initially we began with 1 sensor, made measurements from the brain, and have over time, led by Matt Brooks from the School of Physics and Astronomy, developed a system which is now being commercialized and which is being widely used. So there's a lot of synergy between work in the ultra high field scanner and work with OPM Meg, which we're really looking forward to exploit. So just to finish, the project is underway. We're working with Tesla, Philips, iMedco, and the University of Glasgow to develop this system. I'll come back for those who are interested to describe the performance of the system. But just a little bit about the magnet before I finish, that it's a system that uses a conventional superconductor as found in the vast majority of MRI scanners around the world, which is an advantage. But to make it work at 11.7 Tesla, the wires have to be cooled below liquid helium temperature to 2.5 Kelvin in this case. And that's going to be done here with 4 refrigeration units. So we don't have to, I guess, draw helium off. It should be a 0 boil-off system. We're expecting it to be delivered in December 2026, the magnet, and then subsequently integrated. It's a bit of a beast, the magnet, and it has to be surrounded by an iron shield, which is 567 tons in weight, to shield the magnetic field from the outside world. So we're looking forward very much to the work in this going forward. At the moment, it's a building site, but things are starting to come into shape. You can see where the magnet will go. So I hope that that system and some of the other things I've talked about will form a platform for future collaboration between University of Nottingham and University of Washington. And thank you very much for listening to me and for your welcome.
Always marvelous. The whole journey of MRI, and especially the contribution from Nottingham University and Peter Mansfield, especially. Are there any questions? Right there.
I'm assuming you're kind of picking up.
Is that me or me? Excuse me. Yes, so yeah, we have, in specifying the system, we've asked for the strongest gradients we can get to try to limit the distortion, the most powerful shims that are possible in such a system to reduce those sort of distortions in the magnetic field. And obviously, the platform for scanning to make the possible measurements as least sensitive as possible to those distortions. So it's something that we're tackling and others are tackling at 70. I think things have improved over time, and those developments are certainly being rolled out at the higher field.
Bay? Yeah. The question that was asked is the role of AI for image processing and actual impact on the MRI.
Yeah. So I think all of the manufacturers are now using AI in the denoising of data that's acquired and improving the resolution. So that has already gained a lot of traction just on the scanner. Clearly, there's loads more that can be done in trying to, I guess, improve the measurements based on analyzing large data sets and taking that learning into the way the images are acquired and also, of course, the way they are interpreted. So I think it's already having a significant impact in the way in which the scans are done and the ways in which they are interpreted. And certainly there's a huge amount more that can be done, I believe. And I guess that applies at a low field where one can, maybe gain information from measurements made at higher field to help you interpret where you have a lower intrinsic signal. But I think it will also benefit the higher field as well. We can apply those same effects to accelerate our measurements, which will hopefully reduce the effects of distortions, which is the way forward. But thank you.
Thank you for a wonderful talk.
Yes. So there is a 10.5 Tesla system at the University of Minnesota, which has been in operation for some time. They've done a very comprehensive analysis of the monitoring of the effects of people who have been scanned, looking at blood pressure changes, looking at, I guess, vital signs, cognitive tests before and after, to really show the safety of that. The 11.7 Tesla system at Neurospin, they did a study where they scanned a group of people, and for half of the group, they actually turned the magnet off. And so pretended to scan those people and did the comparison of those two groups and found no significant effects. I guess the effects people worried about in the early days, many things, in fact, that you wouldn't get RF inside the body above 10 megahertz, but the effect we always have to worry about is the deposition of power from the radio frequency, which is well managed, and we have very good techniques for doing that. The higher magnetic field, people worried about the effect on magnetohydrodynamics of blood flow, but that has been established to be, the limit is very much higher. Some people do feel is vertigo if they move sort of quickly within the magnetic field. There's some interaction thought to be with the dark current flowing in the vestibular system, a small force on that. So it's we manage the speed at which we move subjects into the scanner. Some people experience that. Seems to depend on the vestibular anatomy as that. So yeah, there. I'm probably not the best person I'm not a clinician to comment. Certainly the range of techniques we're able to now apply, I think, to making those kind of measurements is probably moving us closer to that. But I wouldn't want to be definitive about that, given my expertise as a physicist rather than a clinician. Maybe our chairman probably knows a lot more than I do about this.
The interesting paradox is the technology is moving so fast. We don't even have clear understanding of a lot of what you see. What are the ramifications on care delivery? It's so much data we have available. We are trying to parse out and see what that data means actually. So there will be tremendous innovation and growth in the data integration and application of not just MRI, other imaging techniques to come up with better diagnostics and better analytic tools as we drive towards precision medicine. I have a question. And first of all, fascinating talk. And, MRI is now so routine, like it's fundamentally transforming many aspects of the care delivery. But also it creates unique challenges. Now the access for MR is a huge challenge all over the world. Mm-hmm. And then we have these great images, but we don't have enough people trained enough to interpret. And I know in UK there are huge backlogs right now. Do you imagine a future where we will be moving to more quantitative imaging and then using the quantifiable data for more decision making?
I certainly hope that the kind of sequences we've talked about and shown, where you can get something which is validated as a number from a scanner, and you can expect to get that same number on a similar system from similar field system from a different vendor, will hopefully help us in that kind of diagnosis. In terms of the people, we surely need to train more people to operate the systems. It's definitely a problem in the UK to encourage people to come in and I suppose help them have a career in that kind of approach.
We are recruiting some of your people from there.
Yes, yes, of course.
We're gonna continue our discussions with our panels afterwards, and thank you everyone online to join us. And I think for the audience, if we could move to the reception upstairs in the Vista Cafe. Thank you.